So welcome everyone. My name is Brandon Wood from Lawrence Livermore National Lab. This is the use case 3 breakout session, panel discussion on energy storage beyond batteries. A little bit about the purpose of this session. So when we were organizing this summit, there was some discussion about the Energy Storage Grand Challenge more broadly. And for those of you who heard Michael Pesson's talk yesterday, he mentioned that there's different thrust areas within that Energy Storage Grand Challenge. The first of which is bidirectional electrical energy storage. That's where batteries sit, and historically that's been the focus of this summit. But the second piece of that is chemical and thermal storage. And I think as things are evolving and the use cases are evolving and the interest in these other technologies is beginning to grow. Personally, I worked in hydrogen even back in graduate school and have seen a lot of ups and downs. And those of you who have been around longer than I have probably seen even more ups and downs. And it's very exciting to see the interest that's beginning to grow again. As people are starting to realize how powerful that technology can potentially be. So we decided to convene this use case panel that would give a voice to these other technologies that are perhaps not as visible and not quite as much research emphasis in them right now compared to batteries, but are equally interesting. So let me just go over briefly some logistics of how this session will work. So I'm going to begin by allowing each of the panelists to give just a very brief introduction as to who they are and their organization that they represent and what their role is. And then we'll go into these deeper dive presentations that each of them has prepared. We have a wonderful distinguished panel of 4 people plus myself. And after the presentations are completed, then we'll open it up to audience Q&A. I would prefer that we save the questions to the end after the presentations have been completed, but feel free to go ahead and enter your questions at any time in the chat box, and then I'll go through and select from those during the moderated Q&A at the end of the talk. So with that, why don't we go ahead and do the introductions one by one. So John, do you want to start and just give a brief summary of who you are and the organization you represent? You're muted. So it should be, I think it's at the bottom of the screen. It's the mute, unmute. So maybe we'll move, we'll keep going through then. Let's move to Ron and we'll come back hopefully to John.
Yeah, hi, good afternoon. This is Ron Kemp from Southern California Gas Company. I work in the, what we call low carbon resources R&D group. So we're developing obviously lots of alternatives to natural gas that are low carbon. So everything from forms of renewable gas to synthetic hydrogen, synthetic methane, that sort of thing. Power to gas, of course, is one of the things that we're involved in. So, we think that we have one of the world's largest batteries, which you'll see a little bit more about. So look forward to presenting and hearing your questions. Thanks so much.
Great, thank you. Marissa?
Hi, everyone. Really excited to speak today. My name is Marissa Sweeney. I'm a director on the investment team at Generate Capital. If you're not familiar with Generate Capital, we are a financing group that is majority focused on funding assets within what we call broadly the sustainable infrastructure space. I would say, as it relates to this panel, I'm going to spend some time talking today about some of our long-term strategy in the hydrogen market specifically. but just know that we invest across a number of areas, including more traditional solar, battery storage, fuel cell, anaerobic digestion, and a variety of other spaces.
All right, thank you. And David? So you're also muted, David. Any John or David, any luck with the audio? I unfortunately don't have unmute privileges, so yeah. John, maybe you want to do the same. Do you want to leave and come back and see if that resets your audio settings? Why don't you leave and rejoin? Let's see if that works.
How's that?
Yeah, that's great.
Okay, great. Sorry about that. Yeah, good afternoon. My name is David Bierman. I'm one of the co-founders and the CTO at Antora Energy. Antora is a pre-commercial hardware technology startup developing extremely low-cost, reliable, safe, long-duration energy storage using an ultra-high temperature thermal energy storage system paired with a high-performance thermal photovoltaic conversion. So it's sort of an all-solid-state approach to getting a huge amount of really low-cost energy storage capacity on the grid, and looking forward to diving deeper into that.
Great, thank you. And then John?
Can you hear me?
Yes.
Excellent. So happy. My name is John Grosh. I'm actually the Deputy Associate Director in Computing in the Computing Directorate at Lawrence Livermore National Lab. So I have two roles at the lab. One is responsibility for overseeing software engineering research in the directorate. And then second is that I have several roles supporting DOE Grid Modernization Initiative and the North American Energy Resilience Modeling Initiative at DOE headquarters that involve large-scale infrastructure modeling and energy systems modeling efforts. And so, those are kind of the things in my job jar. Thanks.
All right, great, thank you. And then I'll finish with as I said, my name is Brandon Wood from Lawrence Livermore National Lab. I am the Associate Program Lead for Hydrogen and for Computational Energy Materials. I'm also the Deputy Director of the Laboratory for Energy Applications for the Future, or LEAF. So I work in the battery space, but do a lot of work with hydrogen, and that's primarily what I'll talk about today. So you can see from the diverse backgrounds of the panelists, what we've tried to do is gather people who have different perspectives, all the way from kind of the national grid perspective to regional utility perspective to early stage investment and commercial deployment, and also a startup, and then my own perspective as a sort of a fundamental researcher trying to connect with these industries. So with that, I think I will go ahead and turn the time over to John. We'll proceed in the order that I show on the slide there to give his presentation. And you can hear a little bit more about his perspective and what he's doing.
Okay, thank you, Brendan. So when the team here was asked to give a panel on beyond batteries, at least from my perspective, it seemed like this was an opportunity to provide a larger context in how batteries and energy storage fits into overall both the electric grid and the U.S. energy infrastructure and critical infrastructure. And so I wanted to say a few words about, the work that we're doing in modeling within Livermore and across the larger DOE context. One of the things I think is important as I saw some of the presentations earlier yesterday, and just generally engaging in this area, at least in a casual manner. One of the things that's very important is to be able to take these various sorts of technologies, be it lithium ion or flow batteries or what have you, and be able to put it in some sort of context of value, be it in economic or perhaps in resilience or emergency response or other applications. And so that's really where I'm coming from with respect to my presentation. So from a lab perspective, our electric grid program is actually quite young. We really only got started around 2010 or 2011. And one of the big projects that we had was this application of high performance computing and modeling to be able to help the California Energy Commission value storage and demand response. And so what you see here is kind of a snapshot of a very long report and a number of presentations describe a comprehensive end-to-end prototype of a modeling methodology that takes into account some key issues of how one might want to value storage and demand response, taking into account understanding details of weather forecasts in specific areas. And so one of the things that we used is a weather research forecast model to get into some very fine details of being able to predict weather patterns and weather for specific wind and solar sites. And so the other is to be able to incorporate uncertainty into the modeling. So we had used ensemble forecasts to pump these into a production cost model, which then can be used to model basically power production over a course of an entire year. And so in this area here, we worked with IBM and Energy Exemplar and CalISO to, at the time, which was around 2012 to 14, exercise the stochastic production cost modeling capabilities, which were then used to produce these various curves that plot basically, here's an example of a capacity of storage that's installed into the grid and the annual net revenue per storage. So basically calculating some sort of economic value for storage. And then finally ending up with some sort of stability analysis. So, this work was about spread across CEC in the lab was about $3 million worth of effort over a couple years. But from our perspective, it really gave an opportunity for us as a lab to start sinking in our teeth into, what does it mean to actually apply some very ambitious modeling strategies to get at this understanding context of storage with respect to the overall, particularly the California energy system. And so one of the things that, in this exploration that became obvious is that when we did this analysis, and there's a long report that I can give to anyone who's interested, that details the methodologies and the conclusions, is that these analyses can produce results that one could compare different storage technologies to one another. That this has compressed air, flow, and ion batteries. And that, from an economics perspective, is very useful. We also ran into or kind of observed that there are a lot of other directions you could take this to build an end-to-end modeling system that one could provide value for multiple stakeholders, either technology developers, grid operators, or policymakers. And so when we did this was a lot of duct taped and baling wire as far as software, but it really showed to us that there was an opportunity to take advanced computing, advanced modeling, and be able to do something, very sophisticated. So if you think about where Livermore is a lab, and then kind of the lab system kind of evolved from and to, one of the things that you really kind of seek to do when you're developing software is not develop one-off solutions. What you're trying to do is develop generalizable solutions that are applicable to broad domains. And that's a big art form, because software can't do everything, and so you have to be able to understand and scope these sorts of the tooling infrastructure you need to build software and modeling software. And so we developed, starting probably 6 years ago, the lab systems, multiple labs, Pacific Northwest National Lab, NREL, and our lab had developed various sorts of capabilities to couple different models together and to be able to address things like two-way power flow. So this T stands for transmission. How do you couple with distribution? In addition to that, what became obvious is also the requirement to model communications as well. And so we developed this coupling framework called Helix, which allows one to connect codes together, manage the data exchanges between software packages like PSLF or SIME or gas models like ngFast, and then be able to do the time management as these simulations march forward. And so Helix is a open source software package that's available to the community, and it really represents this evolution, particularly from the lab system, of being able to start to build these complex infrastructure models that start to link various facets together. And so when I think about storage and where we need to go with storage, I have a few thoughts at the end, but one of the things that we really haven't exercised in these modeling activities is where does storage sit? So, but as an example of things that we were doing at the lab on the right-hand side, we have a project which is the cyber secure integration of DER, which we use to couple models of inverters and distribution systems with the DER management systems. And so what we wanted to do with this is to understand how various sorts of cyber attacks would impact our ability to deliver power to load, basically. And so this involved coupling a power grid model called GridLab-D, which is sort of equivalent to a code called SIME, and other distribution modeling packages with a communication modeling package. And so this was all enabled by Helix. So this required quite a bit of work to build, but without Helix, you really couldn't pull this off. And so I think from a perspective of thinking about where does storage fit in, that getting storage models and controls generalizable and available to the community to share and use in these type of systems would be very useful. And quite frankly, there's a pathway in which we could integrate, instead of inverter technology, storage models to make that happen. We have other projects that we were doing as well. One of the things on the left-hand side is the use of advanced computing to accelerate contingency analysis. Tony Van Buren yesterday talked a little bit about that. So that's one set of technology is important. And others, you deeper into the play of modeling attacker and defender actions. So the kind of the bottom line, there's a rich set of areas that one could explore with these modeling capabilities that are above and beyond what you see in the commercial industry. And really what we're trying to do at the DOE lab system is to be able to provide the building blocks to attack these very challenging problems for the grid of the future. So recently, one of the big projects that DOE has launched And this really was motivated by former Assistant Secretary Walker. It was right after Hurricane Maria, with respect to their efforts in DOE to support restoration, recovery, and building the island. And so it was observed that, one of the challenges was to have models that actually aid in predicting impact of a major consequential event, such as an extreme event of weather, or it could be a cyber attack or a man-made event as well. And how does that impact the national energy system? And so the observation, Walker's request to the DOE, his team was, well, we don't have these models in Puerto Rico. It made building the models very difficult. Of course, we have better models in the United States, right? Like this is all in play. If we had an event like this, we have the tools to help make these predictions. The answer was no, not even close. And so, when you look at the kinds of things that one needs to do in understanding impacts on the energy systems, you start to need to be able to couple various large-scale models together: bulk electric system, natural gas pipeline system, and communications are examples as well. And so the whole idea is behind NARM is to build an integrated system that analysts can use to perform resilience analyses, looking at vulnerabilities of systems, either from a real-time operational perspective, supporting emergency response, to all the way out to being able to advise industry stakeholders on how to make the infrastructure more resilient. So, my last slide here, just basically if you want some more information, this is somewhat dated, but we have a strategic plan on the DOE website that lays out the whole entire strategy for NARM. But really, NARM is about taking these threats, being able to map these threats in some way onto various infrastructure models, and in addition to that, be able to integrate the latest data sets that are out there, either from the government, such as DHS or Department of Transportation, or from the utilities, in a secure environment that we can do multiple number of functions, predict outages, assess economic options of hardening, to real-time situation awareness. And so right now our status on NARM is that we're in alpha phase. So right now we have starting to branch out and have government users kick the tires on it. Our expectation is this will go into initial operational capability mid next year. At least the initial focus on NARM is on government use only, in particular for resilience of the infrastructure. But one of the things that we really need to work out is how can we get these tools out into the industry so there's a spin out or a societal benefit, in addition to more benefit just for resilience of national infrastructure. So at this point, I'm going to say that's the end of the presentation. I'll hand it, Brandon, over to you. Thanks.
All right. That's a perspective that we don't always get, thinking about the sort of diversity of needs for energy storage when it comes to things like extreme weather, right? Events that are obviously those of us in California have been thinking a lot about lately. So I think we'll move on then to Ron Kent from SoCalGas, who will give us a perspective from point of view of public utility.
Okay, thanks so much. I hope you can see my screen because I can't tell from here what you're seeing.
Cannot.
Okay, let me try this again. I clicked on share the screen. How about application window? Sorry. And did that work?
No.
Okay. Sorry. Let's try it again. So, in your entire screen, share your entire screen, okay? And then, oh. So are you seeing anything of mine?
Not yet.
Hit cancel, try it again.
If you're on Chrome, you may not have set the permissions, or there may be a dialog button you had not selected that's hidden behind another window.
I'm not on Chrome. Not on Chrome. Let's see, I'll cancel again. Let's see if there's anything else to do here. I was sharing earlier effectively, I think. That's what.
You sent me your slides, correct? So I could, if you need to,
yeah,
I can
did.
show them too.
Brandon, I just re-forwarded you the slides so that they're at the top of your inbox.
Okay, thank you.
No problem.
Yeah, I think I have them here.
Well, we could just get going that way.
All right, so I'll go ahead and share. Let's see, full screen mode. All right. You can see that okay?
No.
Nothing's coming up here either?
For a minute, did you expand the slide deck? Because I think when you were in the PDF application, it might have been working.
Okay. I'll try that. Share.
Yeah, it works in that window. And then it went away.
Okay.
All right, we'll do it this way.
All right. So we'll just breeze through this. I've already wasted a bit of time here. So we're the largest natural gas distributor in the US. Been around since before light bulbs. And one thing I wanted to point out, it's 130 or to 135, depending on who's measuring, billion cubic feet of geological storage. That's 18 terawatt hours of electricity if you convert it at 44%. Go to the next slide. So we think we're kind of the biggest battery in California, at least. Can you go to the next slide? Okay, so here's what natural gas storage looks like in the, go back one slide. I don't know.
I think there's a delay, sorry.
So if you could just go to slide 2. Well, this is good. Slide 3, it looks fine. Okay. So again, in the lower, okay, then go back to slide 3. Sorry. Latency. Okay.
Can everybody
the lower
else
48,
see slide?
Yeah, 4,200 billion cubic feet of storage in the U.S. So if you tried to store all of the electricity sales in the U.S., that would be about 15% of it. Okay. If in California, if you looked at all of the California gas storage, it's nearly 500 BCF, billion cubic feet of natural gas. That's about 25% of the electricity demand. And SoCalGas is about 7% alone. So that means we can run, if just on SoCalGas's system, we could run the electric grid for about 25 days. And then if you looked at all of California storage, it'd be a couple of multiples of that. So, quite a bit of battery storage. And this includes the energy required to convert it back to electricity, again at 44%. Go to the next slide, please, slide 4. So hydrogen drivers, when we talk about storage, it's not just natural gas, but we talk about hydrogen a lot. And so that's kind of the energy currency for power to gas. And so it's being driven by greenhouse gas emission mandates, obviously, the advent of fuel cell electric vehicles, and then also the curtailment of wind and solar electricity. Next slide, please. Okay, and here's California law. Obviously, I think everyone knows that, so I won't belabor that. Our goal is to get to 5% renewable by 2022 and 20% by 2030. Go to the next slide, please. And then in terms of natural gas vehicle development, so they're saying, this is from NREL, over 3,000 hydrogen fueling stations by 2035, 3 million kilograms of hydrogen per day, up to nearly 5 million fuel cell electric vehicles, and so on and so forth. So very attractive market being developed. So this is another thing that's driving this power to gas scenario. The next slide, please. And then curtailment, of course, and I'm confident this has been covered previously in this workshop. But, for me, it was kind of shocking. I kept checking the number. Please tell me tell me I'm wrong here. But it looks like it adds up just for this year to date, nearly, 1.5 terawatt hours of electricity, okay, curtailed. So if I was washing my car and I put the hose down and let it run down the street, they would come and give me a ticket. But it's okay, apparently, to bleed off, 1.5 terawatt hours of electricity. That seems to be a tool. And that, to me, is kind of concerning. I would like to see a world where every terawatt or every kilowatt hour of wind and solar electricity has a home that gets a market. If nothing else, we should do, turn on machines that take CO2 out of the air with that rather than just curtail it. And of course, you're going to have a hard time getting people to, install new facilities if they're getting curtailed an increasingly larger percentage of the time. So power to gas may represent a solution to that. Next slide, please. And so here's part of the problem. This is, shows the various price nodes, and you can see a few of the nodes there in the Central Valley and a couple other places are negative. And so, people are saying, oh, this is great. We're going to get this low-cost curtailed electricity, but it's kind of this purple unicorn that people talk about it, but no one's actually ever seen it. If you can have a great battery, but trying to get electricity from, say, Central Valley here or wherever to wherever your battery happens to be located is just not quite feasible. And if you were able to do it, they would charge you retail rates. So it's kind of something that's out there as a possibility maybe, but it's not practical today. And so what we need is people like the folks working at Lawrence Livermore Lab to do software magic and come up with software that manages the grid of the future so that, again, every kilowatt hour of wind and solar has a home. Now, I would like to make curtailment punishable by 10 years in prison, but that's why they didn't put me in charge. Just joking. Next slide. The suspense is building for me too. I don't know what's going to show up. But there's challenges with hydrogen. Obviously, the energy density, it's only a third as energy dense as natural gas. So that means if we converted our whole system to hydrogen, we'd only be delivering about a third of the energy. So that's a problem. If we got to 20%, we'd probably take a 13% hit on energy delivery. So it's a concern. Obviously, compatibility with existing systems is an issue. Cost, okay, this is a good thing for everyone to know. $3 per million BTU, which is a common cost for natural gas, is equal to 1 cent per kilowatt hour for electricity. So, you know, when you tell someone that, you know, you're someone living in the Central Valley, living paycheck to paycheck, and you tell them, oh, we're going to switch your energy to electricity, so all of a sudden now the cost for heating their home is going to go up multiples. So we need to get this low-cost electricity, or get electricity that, you know, delivered so that it actually is competitive with natural gas. That's the only way people are going to switch it. That applies to hydrogen as well. It needs to be competitive with the incumbent energies. Otherwise, it's not going to get adopted. And then obviously dependent, you know, the whole hydrogen market is kind of dependent on low-cost electricity, you know, if they want green hydrogen. And then, of course, intermittency is an issue. It's hard to develop a system to make hydrogen if it's going to have a poor duty cycle. And then I mentioned, you know, the kind of the antiquated dispatch system, so you can't really get the low-cost electricity delivered to your battery, whatever it is, when you want it. And I mentioned the low duty cycle of electrolysis systems. Next slide, please. And so people talk about it, water electrolysis, and a lot of people really haven't seen anything since they left high school. This on the far left is a PIM stack, PIM electrolyzer stack. The second slide over on the top, it shows looking down the row of a bunch of stacks. This is the largest electrolyzer installation in the US, to my knowledge, 2.4 megawatt hours. And then, you know, everyone talks about, oh, we're going to drive down the cost of electrolysis, but there's also other things, you know, the balance of plant, so the switch gear, the rectifiers. I mean, this place has a whole building just for rectifiers. It's called the rectifier building. And then the rectifiers give off heat, the electrolyzers give off heat, so you need chillers. And no one's running around driving down the cost of chillers, frankly. So it's hard to reduce that cost. And then high pressure storage. I know there's a lot of work, you know, going on to kind of reduce that cost. And then compressors. There are some electro kind of PIM style compression systems that are coming up. So I have some hope to drive that cost down. But this whole electrolyzer system takes about a quarter of an acre to half an acre of land to put in place. So, and it's stick built, so you have to hire an engineering firm to design it and certify it and get it permitted and all of that. So it's not a trivial task to get these things going. And if you want to do thousands of them, you know, it's going to take a lot of progress in this whole area. So something to think about. Next slide, please. Blue hydrogen strategy. So, you know, the move to, you know, kind of not perfectly green, but low carbon hydrogen is something we're working on. What we're looking at is low cost modular point of use, electric driven steam methane reforming. And you'll see something like that in a moment here. Co-production of hydrogen and solid carbon, so methane pyrolysis. So you can produce carbon black and hydrogen. So you can monetize that hydrogen, monetize the carbon, sell the carbon for, say, tire manufacturing, paint, pigments, and that sort of thing. And then also monetize, of course, the hydrogen. And then methanation, if you can't do anything better with the hydrogen, you can turn it into methane, which is a pretty good energy currency. Next slide, please. So I'm going to talk a little bit about some hydrogen production technologies that I've just alluded to. So you can go to the next slide. And so here is our small solar-driven hydrogen production system. We call it STARS, Solar Thermal Advanced Reactor System. It's in the dish there, you see the focal point of the dish, that's the nacelle, and inside the nacelle is a compact steam methane reforming system. It's based on microchannel architecture. It's very efficient. We think we created the world's, achieved the world's record of solar thermal to chemical energy, 70%. Maybe someone's beat that, but I'm not sure. And then, of course, that compares favorably to PV, to electrolysis. So it's not a bad way to go. The carbon intensity is low because, again, we're not using natural gas to do all the heating. We can use solar energy to do the heating. And but I admit we have not certified the pathway yet. So the next slide. And so this is the kind of intel inside of our compact steam methane reformer. The vertical piece of metal there in the center of that picture, that's the heat exchanger. The disc at the bottom is the reactor itself. Inside that reactor are many mesochannels and microchannels. Those get filled with a support structure for the catalyst, and then the system is then sealed up. So just to give you an idea of how it works, the steam and methane enter at the top right, let's say, and then it goes into the bottom part of that disc, and then from the center goes out, and then it gets flipped around, and it goes back the other direction, gives up its heat, up the heat exchanger and out. Now the heat exchanger is made out of stainless steel, and that's 3D printed, and the disc itself is made out of Haynes, and that is 3D printed, and it takes just a couple of days to do that work. So we can make changes in the design. We can do all sorts of things. So what's significant about this, besides just its small form factor and the low cost, is we are now integrating this with induction heating. So when we apply induction heating, we can do the same thing with the sun. We can either work it so that the induction heating is on that top side and the sun hits the bottom side of that reactor, or we have 2 reactors and we just heat both sides with induction heating. And so when you do that, you get kind of a renewable attribute because the reaction itself is endothermic. So you do pick up the solar energy that you put into it, or the electricity that you put into it in the final products. You can go to the next slide, please. That, while we're waiting for it to change, I should say that that disc, so 12 inches in diameter, 1 inch thick, it produces about 33 kilograms of hydrogen per 24 hours. And so our skid has 5 of those, and it fits in a skid with the gas shift reactor and so forth, the balance of plant. It fits in a skid about 4 feet by 4 feet. So very compact size. And then this kind of shows the thermodynamics, balance, the energy balance of it. And it kind of illustrates that the solar energy ends up in the output. And if you get the copy of these slides, you can check the math there, but it does work out to about 20 to 25% solar attribute in the product that comes out. And so again, we've done this without creating any local criteria pollutants. It's very clean, and we can either do this again with solar or with electric induction heating, or both. Next slide, please. And so here's something completely different. This is kind of a rudimentary lab photograph. We have a much more advanced system than I'm showing here, but I can't show it for intellectual property purposes. But basically, we have a wire inside this vessel. We're putting steam and methane in. The wire creates this corona discharge plasma, and we're able to do steam methane reforming not at 900 degrees C, but at 400 degrees C. And it can be turned on and off really efficiently. again, manufactured cheaply. I apologize. People are working next door, so you might be hearing some other noise. I apologize for that noise. Anyway, this is an exciting project was developed by SoCalGas and the Jet Propulsion Lab in Pasadena. And it's now, we've got this more advanced version being tested at Seton Hall in New Jersey. So next slide, please. And then I talked about co-producing hydrogen and carbon. These are some of the things you can do with it. We have projects where we're making carbon nanotubes and carbon fibers and that sort of thing, and producing hydrogen. So we're kind of excited about the prospect of that, of taking our gas, turning it into hydrogen and high-value carbon. And this table shows you, the various products, the size of the market, the value, and so forth. It's worth looking at closer, perhaps. And I want to mention that Monolith Materials has a methane pyrolysis plant running actually in Nebraska. So that's very exciting. Next slide, please. Methanation is another approach. Here's the Opus 12 reactor. We put in CO2 and water and electricity, and we get methane out. I think I'm running short on time, so I'll just point out that that's a pretty good approach to do it electrochemically. And then the next slide. Integrating water electrolysis with biomethanation. This is a project that a lot of people are aware of at NREL in Golden, Colorado. We're feeding hydrogen and CO2 to these microbes called archaea, and they're converting it into methane. It happens at very mild temperatures, like 70 degrees C, so really a nice solution if you want to make methane. And the map there shows that there's no shortages of low-hanging fruit when it comes to CO2 available. So we should go after these ethanol plants there and make methane out of them using excess wind and solar or dedicated wind and solar systems. Next slide, please. And then this is the next step. It's instead of having water electrolysis plus methanation, there's a process that we're working on right now at Lawrence Livermore, where it's one step. We put in electrons, and we feed electrons and CO2 to these microbes, and they make methane. And the details are described there. The real key is to have really high surface area. So this is something that Lawrence Livermore was able to do, is create these electrodes with kilometers of surface area in a very compact size. So we get really good transfer and energy density. So very exciting project. I think this could be deployed, say, at wastewater treatment plants and anywhere you have some biogas coming out. So you can, instead of emitting the CO2 into the air and separating out for methane in a biomethanation or a biogas plant, you can then simply convert the CO2 into additional methane. Next slide, please. I think that's it. Okay, thank you very much. Apologize for all the glitches here. But
all right, thank you, Ron. I think it was neat to see the breadth of different production technologies that you guys are doing pilot demonstrations of. Marissa, do you want to go ahead and show your slides?
Yeah, absolutely. Give me 1 second just to get set up. And can you guys see my PowerPoint? It should be sharing.
Yes.
Yes, no? Great. Awesome. So I know that we're looking to do Q&A for a bit, so I will keep my remarks relatively brief. But here, let me just tee up for y'all what Generate Capital does, who we are, for folks who may not be familiar. If you're a fan of the Energy Gang, you may have heard from our president, Jigar Shah. He's a pretty vocal voice in the industry, and he has done a lot to talk through kind of what he sees as the future of hydrogen and other markets beyond traditional battery storage. So what I'll spend some time doing today is talking about our role at Generate, how we think of ourselves as fitting into the financing market, and then talking through how we're really looking forward to the future in terms of what's kind of on the horizon beyond battery storage. And really for folks in the audience who may be entrepreneurs or considering working on earlier stage technologies and applications, or really just interested in this use case, kind of some of the takeaways that we've seen as investors evaluating the swath of things that are in the space. So I'll tee it up. In general, we view the resource revolution as anything that ranges from energy storage, power production, green hydrogen production, so on and so forth. And we believe this is a huge opportunity. So that's kind of why as Generate Capital, we have to constantly be looking at the deals that are in front of us and down the fairway from a project finance perspective, but also looking ahead to what will be kind of the next thing that's ready for project finance in the next 3 to 5 years. And I think that hydrogen quite fairly falls into that category. And just to give you a sense, project finance really just refers to a maturity of financing, kind of post-venture capital stage. As project finance investors, and this applies to Generate Capital as well as a number of infrastructure investors, it really relates to the fact that a project can kind of stand alone. Most of the technology has been de-risked, and there are contracts either on the offtake and input side that allow the project to run for whatever the useful life or reasonable useful life that can be underwritten. So as I think about emerging technologies, such as in the hydrogen space, one important part is of course, ensuring that the technology works. But as we start to think about market development and as investors really evaluating the opportunity within the space, we want to make sure that we're tracking kind of how much can be done over a 3, 5, 10-year period. Our markets, as I mentioned, span across all of these areas. We tend to think about our verticals in terms of sustainable power, sustainable transportation, and then sustainable waste and water. And what I think is really interesting about hydrogen specifically is it kind of spans different aspects of these 3 verticals, and there's just a variety of use cases that we can think about in terms of them being interesting and also sharing adjacencies with some of our existing assets. So we're currently active in the fuel cell market. We have a very public partnership with Plug Power. They supply hydrogen fuel cells for forklifts mainly, but in addition are also working on a variety of hydrogen applications. And we really view ourselves as a fundamental partner in terms of understanding their technology and also working with them to understand how things will move forward in the future. On the electrical vehicle side, I think we see a pretty big opportunity in the use case for hydrogen as it relates to mobility for heavy duty industrial activities. So the way to think about that is you have a heavy industrial process where you could use electric batteries in order to deal with that. But if you have a more specific route and you can add hydrogen fueling infrastructure along that route to allow for those vehicles to be more efficient and move forward, that's potentially a use case that's really interesting. So again, I'm largely just trying to contextualize our existing asset base to how we think about the strategy moving forward. And what we kind of think about in general is that the infrastructure transition that is currently underway is going to focus on these 4 Ds. You've probably heard them before, but I'll run through them. It's decentralized, it's decarbonized, it's digitized, and it's democratized. And as you think about market building for technologies beyond battery storage, I think it's sometimes helpful to frame the market through each of these lenses, since this is what many folks within the industry think will really drive investment in the future. So I think in terms of hydrogen, we're already there in terms of decarbonized, right? Assuming that we're able to use renewable power to generate hydrogen, that will go a long way in using other power sources that could otherwise be curtailed, or unlocking a broader market. And from our side, we look to deal with market entry as we work with developers who may have projects that they want to bring forward into the marketplace. I think for earlier stage technologies, those relationships with entrepreneurs often are starting at the time where they're accessing venture capital markets and maybe are not quite ready for project finance. But we look to understand what businesses at that earlier stage are doing, so that we can either, one, just kind of like get involved and understand what their overall business model is, be as close to the innovation as possible and understand like what the market is seeing as far as the future, but then also ensure that we're kind of giving guidance as far as how to make projects and applications and use cases ultimately more investable. Because our goal is always to invest in projects that provide a long-term return that is sustainable and able to be deployed across a number of sectors. We also look to lower costs through economies of scale. And again, our thought here is that if we get in early on a pilot program for a proven technology, we'll understand it even better, such that we'll be able to underwrite it in the future at ideally a lower cost of capital, which is beneficial to both the entrepreneur and also allows for an expansion within the industry and overall deployment. I'll run through these really briefly. Decrease risk. Again, as solutions become more mainstream, they are perceived as safer, unlocking adoption by even more companies and communities. And bankability. And this is, the solution is officially mainstream, widely available, and easy to finance and deploy via traditional sources of capital, like banks. And I would say, in general, Generate tends to operate in these first two bubbles here. I'm not sure if you can see my cursor. And I think for us, when we're evaluating a larger sector, such as hydrogen, we're really trying to take stock of the entire market and the entire use cases to understand like really where we'll play in the future. And as I mentioned, we're really excited about the hydrogen economy. I think it's going to be huge. I think a lot of what our value proposition as a financier is looking to understand like kind of what the common framings are that come out of conversations, and then layering in our own market expertise as it relates to what we believe needs to come together in order to have that solution become more scalable. So as an example, we'll often see folks say like, oh, great, I'll use curtailed renewable energy to create green hydrogen. Isn't this awesome? I have some green hydrogen. It helps deal with grid balance issues and make sure that we're using like good use of the power that we're creating. The only problem with that is that if you're going to create green hydrogen, ideally you have to sell it to someone. So you also have to take into consideration what the purchasers of green hydrogen actually need on the supply side. And that's kind of like that additional market framing that in order for the market to become mature and for projects to become viable, it really needs to be fleshed out. So you either need a very understanding customer, or you need to reframe the problem as it relates to the proper customer or how it could solve a solution for someone else. So that's a really quick example, but it's really just an instance of like things that we often see. Another thing that I think is a bit interesting and potentially relevant for folks on the line, oftentimes we get pitched like folks who are working on like a new widget or a new optimization to existing technology. That is great, like a fancier hydrolyzer that's more efficient and can save money and save costs. All of that is well and good, but if we don't feel that like the market potential is broadly there, it almost becomes like harder to assess like how worthwhile it is understanding that specific widget. And I think to the extent that you're working on an application like that or working on a specific use case, always keeping in mind the broader market framing and really spelling out like why that incremental yield or more efficient process or lower cost option really matters, because without the pieces of the broader market, it can get a little bit lost in the shuffle. And that's it. And I'm happy to answer more questions during the Q&A. Just want to make sure that David has enough time to present.
Thank you. Appreciate that perspective. Yeah, David, why don't we go ahead and run to you?
Okay, making sure you can hear me all right?
Can hear you. Yeah, there's no slides yet, but I don't know if you've shared.
No, I haven't. Let's try this. All right, are we good?
Yep.
Great. So yeah, I also will be brief and really appreciate the opportunity to introduce Antora and what we're doing and the way we think about energy storage. So I'm David Bierman. I'm one of the co-founders of Antora, and what we're trying to do is develop extremely inexpensive long duration energy storage to enable the widespread deployment of renewables. You know, clearly there are increasing places in the world where wind and solar are the cheapest sources of new generation, which is really just incredible. And it changes so quickly. And as everybody, I mean, the reason why we have this session is because it's redefining the entire power sector in ways that we still don't even quite understand. But of course, they're intermittent, and we don't have to really go into that. But clearly, the intermittency causes all sorts of issues on the grid. And I think there's a lot of different ways to think about these issues and different ways to kind of visualize it. But an example is just looking at, at a yearly scale, the variability of the renewable generation profile. For example, this is 2017 on the CAISO grid. And a lot of people look at this and I think correctly say, hey, storage can solve this problem. And I think they're right, but at Antora, we think it's more nuanced than that. For example, if you could put this generation into 4 or 8 hour bins, the overall variability of this system is really hardly reduced. And, of course, you solve other problems, daily ramps and all sorts of grid services, but it isn't really until you can store multiple days worth of power that you can begin to wrangle these inherently variable resources and convert them into a more traditional looking dispatchable generator that obviously the modern grid was built around. So this type of kind of multi-day energy storage, we refer to that as long duration energy storage. And it's quickly becoming a lot more than just a niche topic. Antora has recently partnered with the California Energy Storage Alliance and a bunch of other long duration storage companies to model the 2045 electricity grid in California to better understand the implications of this type of asset class, this long duration storage, that it has on a rapidly decarbonizing grid. And the results are very clear. I mean, they show that over 45 gigawatts of long duration energy storage capacity would provide Californians with the lowest cost way to meet the really critical and important goals of SB 100, saving ratepayers over like $1.5 billion per year relative to the other approaches. And it's not just an academic study. Just last month, I'm sure many people are aware, leading group of CCAs in California came together and announced a 500 megawatt commercial procurement of long duration energy storage, which shows us just the very beginning of what is going to need to be an astronomical uptick, frankly, in long duration capacity to meet, again, those very, very important climate goals. But building a battery that can address these needs is incredibly tough. And it all really comes down to asset utilization. So with long duration storage, you want the energy capacity of the system to be very large relative to its rated power. But that just means that to maintain a particular levelized cost of storage, or the cost to move a kilowatt hour through the system, then for increasingly longer discharge durations, it just requires a reduced capital cost because the total energy capacity of that system cycles fewer times each year. And if you look at existing battery technologies, I mean, they just simply don't fit the bill. Lithium ion, obviously the dominant incumbent energy storage technology, is used for much, much shorter durations. And that's not a technical limitation. It's just purely based on the cost structure of the lithium ion battery. And even we see optimistic predictions, and I totally believe that this is where we're heading, for lithium ion batteries, all in at $100 a kilowatt hour, just still so far away from, for example, the DOE's target zone to deliver very low cost and reliable power. So this is really interesting. I mean, it creates this huge technology white space that, if you could address, could really just convert intermittent renewables, which are cheap, into pure formed and shaped power that the grid needs. And so Antora is trying to develop a technology to bring system costs all the way down to the floor. And that is the kind of thing that we think can enable profitability for projects with assets that, again, can only fully cycle just a handful of times each year. So I just want to briefly introduce kind of what we're building. And the approach is relatively simple. So in our system, excess electricity from the grid is fed into the device, and it's used to resistively heat an ultra low cost and readily available storage medium, raising its temperature to like thousands of degrees Celsius to the point where it intensely emits thermal radiation internally. And at a later time, when we need power, we introduce a photovoltaic cell, like a solar panel, to actually absorb and convert this emanating thermal radiation back into electricity. So it's electricity in and electricity out, just like any other battery in the world. But we're storing the energy intermediately in the form of heat. And this has two really, really important advantages as we see it. So the first is that we're able to store energy in one of the cheapest and most abundant materials on the planet, petroleum coke, which is a waste stream in oil refining. And the second is that instead of very large conventional thermomechanical generators to reconvert the stored heat into electricity, we can instead leverage the photovoltaics industry. So, the decades of work and hundreds of billions of dollars that have already been spent to build up today's booming solar markets. So to realize this system, we start with a really well-insulated box as shown in this cartoon, and you fill it up with our cheap and abundant storage medium. And then an array of slots are engineered inside the volume to allow us to access that radiant heat energy with our photovoltaic power modules. So you simply insert these modules into the volume to instantaneously generate electricity at any fraction of the rated power of the system with no performance penalty. In addition to just being extremely low cost at long multi-day discharge durations, I think our technology exhibits a couple other really unique and important attributes that I'd love to highlight really quickly. First is about scale. So because of the solid state photovoltaic heat engine, the cost and performance of the power block of this system scales completely independently of power output. That's something that a steam turbine or a gas turbine just can't do. And this enables opportunities as small as say 50 kilowatts and up to massive grid scale with no change in performance. So we can reach very small behind the meter C&I type markets, or we can reach really large solar plus storage utility scale markets in a highly citable footprint that can fit within a shipping container. Next point is about charging. So because the charging mechanism is just direct resistive heating through the graphite blocks, and it's completely decoupled from the photovoltaic discharge, it actually allows us to rapidly soak up enough excess or spilled power or curtailed power in just a few short hours per day when those energy prices are low, that can actually power the system for many days after that. So a very quick soak up with a slow dispatchable discharge, I should say. Another point I just want to address is safety. Of course, this system goes to an incredibly high temperature, but we feel it's significantly safer than a lithium-ion battery. The storage medium itself, while hot, cannot sustain a flame, nor are there any mechanisms in the system for thermal runaway or explosion risk. And finally, the system lasts. With each cycle, we are just raising and lowering the temperature internally of a highly stable material in an inert environment. And then we use a heat engine that itself has no moving parts to generate electricity. So we expect very long lifetimes out of this system, on par with wind and solar assets that you may be pairing this with. So finally, I just want to really commend our team and say, in a few short years, our team brought this technology from a very early concept through a benchtop demonstration of a world record thermophotovoltaic conversion efficiency at the Lawrence Berkeley National Lab to a large 100 kilowatt hour full system prototype, and now have secured funding through the California Energy Commission to build out our first pilot system with a wonderful and dedicated partner in the Central Valley. And to be clear, Antora was able to make all of this progress in this time because of committed partnerships and collaborations. From the early days of Cyclotron Road and the Tomcat Center at Stanford, we were able to advance the concept enough to attract funding from the ARPA-E's and NSF and CalSeeds to dramatically reduce the technology risk facing the concept. And while I'm on the soapbox, as we look to the future, I think it's really clear that in order to bring this transformational energy technology, other transformational energy technologies to market at the pace that is required to address global climate change, we need organizations who are traditionally and understandably conservative to be a little bit more aggressive with emerging technologies. That's asking utilities to pilot systems before they're bankable, incentivizing independent power producers or developers to bid on an RFP with new creative solutions that are frankly untested. And it's even asking the finance world to find more patient capital to bring to scaling up hard tech innovations and infrastructure versus, of course, just funding the next app to try to get to revenue as fast as possible. So I'd better cut it off there. But thank you so much for listening. And I would be remiss if I didn't mention that we are always looking for passionate and ambitious folks to join the team. So if you're interested, or if you know someone who's interested, please reach out to us at hiring@entora.energy. Thank you so much.
Thank you, David. So I think I'm going to forego showing any slides of my own, but I'll inject remarks where appropriate in the Q&A. I want to make sure that we have time to discuss things a little more freely. So thank you all for your presentations. I appreciated the sort of breadth of perspectives. I thought maybe we could start with a little bit, David touched on this at the end as well, but when we think about hydrogen and thermal storage, there's always the 900-pound gorilla of batteries. And to some extent, I think there's a perception, in my opinion, not justifiably, that there's a competition between the two. And so I'm wondering your perspectives from the panelists on how to sell these technologies in a way that doesn't necessarily put them competitive with batteries, but really connects them to the niches that they really make sense for. And then along the same lines, how do we get a workforce that is sort of oriented along these same lines? Maybe we could start with Marissa. You want to provide a perspective on that?
I'm not sure if I'm best positioned to talk on, I guess, like the workforce.
Yeah, we'll say.
Like I like, but I think, I mean, like any. Actually, no. Sorry. Could someone else answer this? I don't think I have the best perspective.
Why don't we go to David then? You talk.
Yeah. Sorry. Just full disclosure.
About the where you're trying to fit in terms of the thermal battery.
Yeah.
Maybe you want to pontificate a little on that.
Sure. Yeah. So, I mean, in the near term, I'm just going to guess, we will see lithium-ion battery eat up all the competition for all grid-scale energy storage up to 10 hours. Just a guess, but the costs are coming down so fast. The supply chains are maturing so quickly that where we want to, if we're competing with lithium-ion batteries for market share, I think we're really in trouble. And so we're not looking to do what lithium-ion batteries can do. We're looking to really slot into that multi-day or week type discharge. Really, I think it's situated somewhere between lithium-ion batteries on the inter-day type scale and something like hydrogen or some other sort of seasonal type solution on the sort of many month scale. So I think, like I said, I mean, there's emerging commercial opportunities in that 10-hour space, but it's a very, very dangerous place for an emerging technology to be when competing with the incumbent lithium-ion battery.
Yeah. Ron, do you have any thoughts on sort of the niche application for medium and longer term storage? It seems that's maybe the sweet spot for these technologies.
Yeah, I think that the technologies we've talked about, particularly hydrogen, is not suited to compete with batteries in short term. It's really not necessary. There's plenty of market, for the longer duration stuff. So lithium-ion batteries should do what they do well, and hydrogen can fill in for the cases where you need this long duration storage. As many people know, in California, you've got wind and solar that are coincident, and they occur mostly in the summertime. So there's a lot of the year that they're underproducing, and so there's the need right there for the longer duration storage. The other interesting thing about it, I think what David presented and what I presented, is that there's not this you're either charging or discharging. With hydrogen, you can be charging and discharging at the same time because your discharge could occur somewhere else with a different machine. So your duty cycle is definitely greater than 50%, whereas batteries, while it's charging, it's not, going to be discharging, and vice versa. Yeah,
this sort of idea of spatiotemporal shifting, right? both in time and in space.
Yeah.
So there's a question from the audience. What is the state of the art for beyond batteries outside the US? So maybe we could talk a little bit about leadership internationally. I know that there's, particularly in hydrogen, there's a lot of activity in the EU, a lot of activity in Asia around this. Announcement from the UK that came out, I think, just a couple of days ago as well. The US seems a little slower, but in how much are you looking to international leadership or trying to reestablish US leadership for some of these technologies? That's maybe a question for Ron and Marissa, probably.
And I can redeem myself to jump back in. I think especially as we talk about building a marketplace that actually works for deploying, regardless of whether it's like an individual state, an individual county, or a straight up like separate country or organization like the EU that creates a model that could potentially work, there's always things to be learned from. I think like the fact that the EU is ahead or that other countries are ahead, or other countries are ahead, is not necessarily a bad thing. And I think that even if it's like set out in a way that wouldn't necessarily work in the US or wouldn't necessarily work in specific regions, it still, at least in some respects, provides a framework and provides an opportunity to like learn from how to do it better or how to adjust it. So I do actually think in that sense, like that's just generally good for everyone. I think for the US specifically though, as I mentioned, like particularly as it relates to if you think about hydrogen as a general, like the hydrogen economy as a concept, there's going to be a ton of infrastructure that needs to be built in order to actually launch that. And that doesn't just like happen out of thin air. Like there has to be enabling pilot programs, legislation, policy that has to come together. But if we have folks like in other regions that are getting the conversation more than started, actually putting something on paper and getting it done, it gives us like a leg to stand on in terms of rolling. So that's kind of how I think about it. That's like again, like the highest level. I'd be curious what Ron or John or even David thinks about kind of looking at the competitive side from more of like, I guess, like the supply side, so to speak.
Mm-hmm.
Well, I think that Europe, of course, is leading on hydrogen in a lot of ways, but it makes sense because they don't have low cost North American natural gas, for example, and they seem to be more politically motivated than we've been. So they've got a couple of things going for them. But in terms of developing the technologies, I think that we are very competitive. And I think that we would utterly fail if we just develop technologies that are used in the United States. We really need to be developing this and driving down the cost so that it actually is competitive with the incumbent fossil energy and can be used in developing nations where most of the greenhouse gases, new emissions are going to start coming from as their standard of living increases. So we really need to think of it as a really economic development, and as well as technology development opportunity and kind of necessity. So we welcome all everyone that wants to contribute. There's more than enough market here for everyone. So it's kind of actually exciting that we are in a position. We're blessed with great problems, huge problems, but we're also blessed with the ability to actually solve them. Not many people can say that.
Yeah.
I just want to echo Ron. I totally agree with that mindset. The other just small thing that struck me about Europe that we've looked at a lot is, you mentioned not being, I don't think you said blessed, but not having, really, really low natural gas prices in Europe. It's actually something that drives them, of course, to look at hydrogen, but also other ways to electrify their heating. So, they're looking a lot, sort of a shameless plug for Antora, but they're looking a lot at thermal energy storage technologies that can very cheaply soak up all that power and then use it to distribute in district heating or in their industrial processes just to reduce their fuel consumption. Again, this is an economic driver too, because they've got cheap electricity and they've got relatively expensive heating fuel. So it's not quite the same dynamic that we have here in the States, but definitely an interesting example of Europe really leading us in that way.
So let's see, Jeremy is asking about flywheels. What do you think about the potential of flywheels? I'm not sure if any of you have perspective on other types of energy? I mean, we focused on, obviously, on hydrogen and thermal, but that's scratching the surface of what's available out there. Do any of you have any perspectives on other technologies?
Unfortunately, Jeremy, not a particularly insightful one. I just, from the perspective of let's get beyond a lithium-ion battery. Let's start to do things that lithium-ion batteries can't do. I really think that we need to think about the cost structure of the energy side of things. And we need to think like if we needed to scale the energy independently of the power, again, just specifically for the use case of how do we deal with the kind of bulk energy storage, I think flywheels are going to have a really tough time in that regard. But I really don't know enough about them. So that's just my 2 cents. And I think that's all it's worth.
Yeah, we sort of handpicked the panel to some extent. But, I do want to bring up one topic before we close, which is focused on partnerships. I mean, to some extent, that's the purpose of this entire summit, is to think about how we can better partner. Speaking from the point of view of a researcher at the national labs, this is of high interest for me to figure out how to really become more engaged with industry. So I'm going to ask the question to all of you, and then speak from your individual perspectives. How to strengthen those partnerships with the lower level researchers, say at the labs or in academia, and what role do you see them playing in the sort of the concept of commercialization? Maybe we'll start at the small scale with David.
Well, we have a lot of experience working with the National Lab very productively. So when Antora was just starting, we were in the Cyclotron Road program. That's a great program that I highly recommend researchers or entrepreneurs to just kind of check it out and see, especially for these really hard technical ventures. But we actually were on a grant with Lawrence Berkeley Lab, working on one of the aspects of our system that was still kind of scientific, and it was a little bit different from our main thrust, but it was a hard problem, and it's a problem that, frankly, is probably not the best place for venture capital, but a really great place for national lab researchers who, again, like want to tap into how do I solve the right problem. And I'm not saying it's like the most relevant problem to get us to market, but it's an incredibly important problem that eventually we're going to need to address. And so we've got really great partnerships with the National Lab, again, funded through the Department of Energy, that I think if we can incentivize partnerships like that, I think that's a good way to, and you'll have to ask them, but I think that's a good way to keep them really engaged and thinking about at least the same problems we're thinking about in a very relevant way.
Ron, I know you've done a lot of national lab collaboration. Do you have any thoughts on that?
Yeah, it's like Woody Allen, showing up is 90% of success. Basically what we did, and mostly it was me, is just humbly just showing up at the national labs and saying, these are our problems. So I went to Pacific Northwest National Lab, spent a couple of days there saying, here are the problems we face, what are the solutions are out there. And, national labs are such a, I call it, America's smartest idea. They're just a tremendous resource. They've got things in files that, could solve problems, but, maybe they didn't realize that, the putting, two things together, here's a solution. So that was very fruitful. I went to Lawrence Livermore, sat there, Roger Ains brought together a group, and Julio Friedman when he was there, and we just sat around and brainstormed, and that, resulted in the projects I have there. Same is true at NREL, with Martha Simcoe Davies, who was reaching out to industry, and so we got together and described problems. And so we have distinct, actually, at this point, we have distinct projects at those three national labs, and some bleeding over into others. But and then also, going to places like Caltech and just saying, like, here's our problem, let's do something. People, when we talk about kind of solar chemical solutions, for example, people don't really believe it, like it's not realized. I just challenge them. We need to actually make something, a device, and show that it can be done, so that we can actually get funding. And that's another part of it, is putting in some seed money and doing some work with the national labs, and then getting enough accomplished that then you can take it to DOE and you can say, hey, here's something you might not have thought about. And, sure enough, a FOA comes out that, in 6 months later, that actually works. It applies for this to that concept. So those are kind of my experience.
Thank you.
It's been very, very rewarding, though, I will say.
So Marissa, I know you have to leave. I don't know if you want to say anything briefly, or otherwise I can.
I was furiously typing my comments, but I was going to say, I think actually, it's hugely valuable from the project finance space. Like, we take complete benefit for all the work that is done in national labs and all of the funding that comes in that early stage, because that's really none of it would be possible without getting over that initial technical hurdle. I do think, though, from a marketing perspective, even more so, sometimes a challenge, even when there's a technology that works, proving out a use case or a market case for the technology. If you think about inserting something like a hydrolyzer that relates to hydrogen into a specific commercial application, it may not be immediately obvious what the value proposition is for the customer. So someone might not be incentivized to work on it. Whereas I feel like from a national lab standpoint, through different partnerships, you can actually have this ability to almost prove out the use case without the commercial considerations that would be necessarily required for an average developer or even an average technology manufacturer. And even if the costs don't make it work today, it's not today commercially viable, at least can show what's possible. And through those sorts of white papers and demonstrations of use cases, it can kind of give folks the idea okay, here's what I need to believe in order for this to be viable. And I think even that first step of conceptualization is huge. And frankly, folks are not always incented to work on the things that are 4 or 5 years out. Whereas you have that flexibility to take that longer term view and provide a framework for folks who are trying to bring things down the adoption curve. And that's huge. And that's why I always geek out, and I'm always reading reports about kind of future adoptions, because it kind of helps someone out like me who looks at kind of the later stage of things, get out of my underwriter shell and start thinking okay, but we're really talking about a 5 to 10 year transition. What does this actually mean? What has to come into play? How do you overlay a market view that's inclusive of everything happening on the front end, plus kind of the realities of what we're working with in the real world, which currently is a low natural gas pricing environment. So that's what I would say.
Thank you. Appreciate that. So unfortunately, we're out of time. We need to jump back into the other session. I'm going to leave with one closing thought that I think ties in a lot of the perspectives we've had today, which is that one of the things that I'd really like to see from a kind of materials researcher point of view is better integration between the use case, the system design, and the materials design, which are all, I think, intertwined, and people tend to work in one or the other. And I think it's a nice illustration of the people we brought together today in the panel that there's really a lot of benefit for communicating across those lines. So please join me in thanking all of our panelists, and we'll go ahead and release back to the roundtable discussions.